Okay, so we're going to start a new topic called dynamic programming. This is going to be, I think, a short topic. I think I only plan to talk about it today. I guess before kind of introducing this, maybe it's good to kind of think philosophically about, what makes it hard to solve certain problems. So for example, let's suppose you're coloring a graph, right? Let's suppose you're trying to color it with three colors, red, blue, and green. Okay, I mean, take the first vertex. Like, let's suppose I'm somehow processing the vertices in order. The first vertex, I don't really care what I give it. It could be red, right? Second vertex, so maybe it's a neighbor of the first one. So I can't give it red, but I don't really care. I could give it blue or green. Doesn't matter. That's sort of up to symmetry. But at some point during this process, you're going to have to make a choice, right? I mean, I haven't really made any. These choices are kind of arbitrary. It doesn't really matter. But eventually, like, maybe you reach this vertex, and it's like, okay, I can't give it blue, but I could give it green or red. And if I give it red, that's going to be possibly different than giving it green. And maybe if I give it red now, and I keep trying to color the graph, maybe I'll color 90% of the graph and realize I can't continue. Because maybe some vertex gets a red, blue, and green neighbor, right? And then maybe if I would have made it green and made some different choices throughout the whole algorithm, maybe I could have finished, right? And I guess it's hard to know, if you start making decisions early in an algorithm, what are the consequences later? And how far do I have to go back and change my mind and go forward, So I think that's what kind of causes some of these, like an algorithm for a hard problem like graph coloring, to kind of blow up and become out of control, because you have to keep going back and changing your decisions, right? And if you think of like a tree based on your decisions, like for the first vertex, I could color it red, blue, or green. The second vertex, I could color it blue or green if it's a neighbor of the red one, or whatever. And but you could think of like all of the decisions you make, will kind of be affected by the earlier decisions. And if you think of it like this, there's going to be a sort of tree of different decisions you could make where like the number of leaves is going to be like exponential. So anyway, so dynamic programming is basically a method for taking certain problems and kind of breaking them down and analyzing them in a way that the idea is going to be, we're going to kind of not make any decisions. We're going to try to avoid making decisions as long as we can, right? Sort of defer it to later. And in some sense, okay, so in some sense what we're going to do is kind of process, kind of go through the algorithm starting at the beginning, keep making steps, don't lock in any decisions, but each step you make, only look back at a few previous things that you've done earlier, things that you've kind of computed. And then at the end, you'll have enough information where you can make the decision and solve the problem. Okay, that's extremely vague, but let's see an example. So a digraph D is acyclic if it doesn't have any cycles. So it doesn't have any directed cycles. So in other words, you're not allowed. So this is also including kind of cycles of length 2 like this. So no directed cycles. But you can have like cycles that are not like, so these cycles are kind of perfectly directed, like kind of clockwise or something. You are allowed to have, like, for example, something like this is okay, right? Because it's not a directed cycle. There's like a backwards edge. So there's like a shorthand, like a short kind of notation for describing directed acyclic graphs. So people call them DAGs. So a DAG is a directed acyclic graph. Okay. So here's a problem. Let's call this like the longest path in a DAG problem. Okay, so let's say we've got an input which is a directed acyclic graph D, or a DAG, and a length function. L, and we're going to be very general. So usually when we're doing like shortest path problem, we have lengths on the arcs. I'm going to put a length on the vertices and on the arcs. Okay, and I'm going to allow all lengths, like all real numbers, but also so negative and positive. And let's just also include the infinities, so like negative infinity up to positive infinity. Okay. And then our goal is to find the longest path in D with respect to this length function, where the length of a path is the sum of the lengths of the arcs and the vertices in the path. So length is the sum of a path of the lengths of the vertices and arcs in the path. Is the statement of the problem clear? Okay. So if I didn't have any, so in this problem we're only considering directed acyclic graphs. If I didn't have this constraint that it's acyclic, we'd be screwed because suppose even we just take a graph, right? Like a graph you can think of as like kind of a directed graph where every edge is like corresponds to one of those. Could I possibly solve the longest path problem in a graph? And the answer is no, because I don't know. On one of your assignments, you kind of there was this thing about like Hamilton cycles and Hamilton paths, right? So if I gave you a graph and you had an algorithm to find the longest path in that graph, you could determine if it has a Hamilton path, because if the length is n minus 1, it's a Hamilton path. So yeah, this is, if I didn't have this condition that it's a directed acyclic graph, this would be a hard problem. But also, actually this problem, I should also say we already know how to solve this kind of in a fairly short amount of time. Because remember there was this thing about conservative length functions, that if there are no negative cycles in the digraph, then you should be able to solve longest path, shortest path, any of these sorts of things. And you also gave a linear program that solved that on one of the assignments. So if you have an acyclic digraph, it doesn't have any cycles at all. So it definitely doesn't have any negative ones. So it's conservative. So you could solve this with the Bellman-Ford algorithm, or using the linear program from the assignment. But what I want to show is that you can solve this much faster if you know that it's a directed acyclic graph. Okay, so So basically, we're going to find an algorithm that, like, it's hard to imagine anything that could go faster than this algorithm. Okay. So I guess a theorem is that this problem can be solved in time big O of the number of vertices in the digraph plus the number of arcs in the digraph. And yeah, the point of this is that even though we could have solved this with Bellman-Ford or linear programming, I'm pretty sure that the solution would not, like the algorithm would not be this fast. This is significantly faster. And like, it's hard to imagine doing it any faster than this, right? Because like even to just inspect the graph and just look at how long look at the length function and look at how long everything is, you'd have to look at every vertex at least once, and you'd have to look at every arc at least once. So like, you couldn't even look at everything without this amount of time, right? So yeah, I think you're not going to be able to do it any faster than this, really. Up to, like, maybe you could improve the constant, but that's about it. Any questions about this so far? Okay, so the approach here is using dynamic programming, which I haven't told you what it is. But I don't have a very good definition of what it is. So essentially the dynamic program is going to be what I'm going to show you right here. Okay. So we will compute the function, let's say h from the vertices to negative infinity to infinity, where h of v is the length of the longest path that ends at v. Okay. The reason I'm using h is maybe the letter h here kind of stands for height. So let's say, like, I don't know, the height of v is like the longest path that ends at v. Okay. And then, of course, if I knew this information for every vertex of the graph, to find the length of the longest path, I just go through the vertices one by one and take the one with the highest value of hv, right? Okay. And also at the same time, we're going to find p of v. So p is going to stand for like the parent. Which is like the vertex that comes before v on that path. Unless v is the first vertex and the last vertex, in which case p of v will just be v. So yeah, where p of v is the vertex that comes before v on the path. So on such a path, unless v is also the first vertex on the path, in which case we're going to have p of v equals v. so at the same time, we're also going to compute this kind of parent function. Okay, and if we know all of this information for all the vertices, yeah, like I said, we would then just go through and find the vertex of the highest height. And then to reconstruct the path, we would take that vertex, and then the parent of that vertex, and the parent of that, all the way down until that'll reconstruct the path, basically. Okay. Okay. Maybe let's move over here. But is it clear that what we're trying to compute? Okay. Okay, actually, maybe I'll write a couple of more things over here. So I'm going to initialize maybe I'll just call all of these things null. For all vertices. Okay. At the beginning of the algorithm, and now I'm going to run the algorithm. Oh yeah, also, okay, maybe I'll write something else over here. Fix an arbitrary order of the vertices. So fix an arbitrary ordering V1 up to Vn, where n is the number of vertices in the digraph of the vertices. Okay. 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 All right, so this is going to be a very short algorithm, but I'm going to basically just run a certain kind of subroutine, and then I'm going to have to explain what this means. So I'm just going to, for each vertex one by one, I'm going to run the kind of subroutine, which I'm calling compute length bi. So the inputs of this function are like bi, the function h and p. Okay, so this is, we need to explain what this does, but so this is to be explained below. And then at the end of this, we're just going to output, you know, yeah, the longest path. Using like h, the function h, and the function p. So just in the way that I said, so what I'm going to claim is that after I've kind of run this subroutine on every vertex, then I can just, yeah, find the vertex of highest height, look at the parent function, and construct the longest path. Okay. Okay, so how does this function work, this compute length function or subroutine? Okay, so what it's going to do is first of all, it's going to look at the height of the vertex v that we've computed so far. And if that thing is not equal to null, well, what this means is that we've already computed it earlier, basically. Like, that's what it's going to mean. In which case, if we've already computed it earlier, we shouldn't compute it again. I don't want to recompute anything twice, basically. So, yeah, then basically do nothing. Okay. Okay, so now let's suppose that it has been computed. So if h of v is null, or sorry, yeah, let's suppose it hasn't been computed yet. Okay. Okay, I'm noticing there's a slight mistake in my notes, but I'm going to just fix it now. So, yeah, so if this height hasn't been computed, here's what I'm going to do. I'm going to first say, okay, maybe the longest path that ends at v, it could just be the path that contains v. So, okay, so I'll first, as a first guess for the height of v, I'll set h of v to be the length at v. So this is like saying that so far, the longest path ending at v is the path that contains v only, because we haven't looked at anything else. So this is like kind of my best guess at this point, and I'll also set the parent of v to be v, just to say like, yeah. I mean, this is a candidate. Just taking the vertex v as a candidate for the longest path, and I'm just going to take that for now. Okay, and now for each, so either the longest path is just the path containing v, or it must, so the longest path ending at v, or it must go through one of its in neighbors. So we'll go through all the in neighbors and see if we can do better, right? So for each u in the in neighborhood of v, okay, of which there could be none, right? There might not be no in neighbors, in which case we would just stop here, basically. So what I'm going to first do is, so here's the thing. I don't actually know if I've computed the height of u yet. So just in case, just so that I make sure I do it, I'm going to run compute length UHP, okay, just to make sure that I've actually computed the height of u before I try to compute the height of v. Okay. Right. So that's all I'm going to do, and then I'm going to choose some in neighbor of v. Okay, if there are none, then I would have stopped earlier. But yeah, so choose some in neighbor of v such that the height of u plus the length of uv is maximized. Okay, so is it clear why I'm doing that? Like the height of u is the longest path that ends at u. And then if I extended that path to include v, I would get an additional LUV. I would also get an additional L of V onto that path, but that's going to be the same no matter which U I pick. So that's going to come into play in a second, but I don't need to really factor that in because every U, like if I extend the path from U to V, I'm going to get a plus LV anyway, like for every, it's the same for all of them. So this is the thing that depends on U. And yeah, if this thing is positive, okay, yeah, so we've chosen this so that this is maximized. If that's positive, so like, yeah, if this is like non-positive, then I should just take the path, the original path I had. If it's positive though, I may as well take, it's better to take a longest path that ends at U, then add this, which will be positive, and then add L of V. So yeah, then set the height of V to be equal to H of U plus LUV plus L of V, which is the length of the path, the longest path that goes through an in neighbor of V, and set P of V equal to U. Okay. Okay. And otherwise, so if this isn't positive, then we would just default to having, yeah, H of V being equal to L of V, P of V being equal to V. Okay. Is this kind of like pseudocode understandable? The concept is very simple, right? Either the longest path, it just includes that vertex V, or it goes through an in neighbor, and like you just want to work out which of those is the right thing, right? Oh, actually, maybe there's something here that maybe I should have made clear earlier, is that what I'm actually doing, like what this is really doing is it's finding the longest walk that ends with V, because we're not keeping track to make sure that this, like if I look back at the V and the parent and the parent and the parent, we're not keeping track to make sure it doesn't repeat vertices. But the thing is, this is a directed acyclic graph. You can't have a walk in that in a directed acyclic graph that repeats a vertex, because that would make a cycle. So yeah, there's a subtle point here that this really does find a path, not a walk, because directed acyclic graphs don't have cycles. Okay. Okay, so what we need to do then is make sure that this is correct and make sure that it runs in time big O of the number of vertices plus the number of arcs. Okay. So I think it's like almost clear by definition that this is a correct algorithm, but let's be sort of careful. So let's claim that this algorithm computes the functions h and p correctly. Okay, and if it does that, then it also correctly identifies the longest path. Okay. Okay, so let V be a vertex of the digraph, and let K be the length, so the maximum number of arcs in a walk in D that ends with V. I don't want to use the word length because length has a different meaning in this problem, right? The length of a path is the sum of the lengths, but yeah, so I want to say k is for this particular vertex v, k is the maximum number of arcs in a walk that ends with v. And we're going to prove that this thing is correct by induction on k. Okay, so like my kind of base case would be like k equals 0, which means like v is a vertex where all of the edges, all the arcs come out of v, nothing goes into v. So by the way, a vertex like this we're going to call a source. It's a source because, yeah, things only come out of it, nothing goes into it. Okay, so now if we think about what happens in this algorithm, like corresponding to v, so like, okay, at some point during this algorithm, like the compute length function for v gets executed. I mean, it could be here, like it could be, or it could be kind of inside of the compute length function of another vertex, but at some point it happens, right? And the first time it happens, the h of v is null, so this does not occur. So the first time it's run, it notices that h of v is null. What it does is it sets h of v to be L of v. It sets the parent of v to be v, meaning there is no parent, basically. And then none of this is going to happen, right? Because there are no in-neighbors of v. So like this is not going to happen. It's not going to choose any u because there are none, right? And it's just going to compute that the length of the longest path is the length of v, and that's correct, right? So yeah, so oh, and then every other time it's run, right, this thing will be non-null, and it's just going to do nothing. So yeah. So the algorithm sets h of v to be the length of v, and p of v equals v, and it and never changes this, right? So, which is correct. Okay, so now suppose k is at least 1. Okay. So yeah, there are some walks that enter v. Oh, and by the way, notice that this integer k is always finite, right? Because in a like we said in a DAG, you can't have self-intersecting walks. So yeah, there's always some finite length. Okay, so in this case, like, I mean, either the longest path is just the path including v, or it must include an in-neighbor of v, and like, I don't know, if you think about it, in either case, it's going to give you the right answer, right? Yeah, so maybe I won't go through analyzing all of this, but basically either the longest path is just the vertex v, or it includes some in-neighbor of v, like by induction. So like this in-neighbor of v, the longest walk that ends at u is at most length k minus 1. Because if it was k, then I could take a walk that ends at u and take one more step and get v, and that would give me a walk of length k plus 1 that ends at v. So, so by induction, like h of u is correctly computed. So and p of u were computed correctly. And I don't know, if you think about it, so it's going to be computed correctly for V as well. So basically it correctly computes H of V based on this information. Okay, that is, I'm being a little bit lazy, but is it clear that it has that property? Like, okay. Okay, so yeah, if we kind of believe this, then it comes down to analyzing the running time. Analyzing the running time is something you've got to be a little bit careful about because of this recursion, right? Like whenever I compute something for the vertex V, inside of that computation, I'm also computing, I'm also kind of recursively running this function on the in neighbors of V. And like, if you're not careful, that could get out of control. Because especially if I'm recomputing things I've already computed, which it's important I avoid that. Like if I was recursively recomputing this for vertices where I've computed it before, like this is going to have a really horrible running time. Okay, so I need to kind of analyze this carefully. So I want to like basically associate the steps of this algorithm to certain vertices. So basically to analyze the running time, we show that we can basically split up the steps of the algorithm. So that, and associate them to vertices. So that the number of, so big O of 1 plus out degree of V plus in degree of V steps are associated to V for each vertex V. And if I can do that, then if I like sum this up over all vertices, that's going to count every vertex like, well, this is like a 1 for each vertex. That counts the out degree of the vertex. That counts the in degree. And if you sum that up over all vertices, that counts the vertices, and then it counts like the arcs twice or something, right? So yeah, if I can associate almost this many steps with each vertex, if I sum that over all the vertices, it's going to be like big O of the number of vertices plus the number of arcs. Okay. Okay. So how do I do that? So here, the idea is basically that, so yeah, when I run compute length for some vertex V, like the danger is this kind of recursive thing that I'm doing this for all of the in neighbors of V. But the steps, like I want to kind of treat the steps that happen inside of here, those do not get associated with V, they get associated with U. Okay? So that's kind of the idea, because otherwise I'm going to be double counting these things, and it's going to get out of control. So, let's see, how do I say this? So for each vertex V, so let's think about how many times is this thing called. So the function compute length V HP is called, like it's run, 1 plus the out degree of V times. During the whole algorithm, right? Because, so the 1 comes from here, the fact that I just sort of blindly go through this and call the function for every vertex. And then for every out neighbor of V, it will call the function once, right? Because it's doing, for every, like if W is an out neighbor of V, then V is an in neighbor of W, and it'll call that function. So right, so this is going to be called that many times. But the thing is, the only time when it does anything interesting is the first time. Because the second time, the third time, et cetera, it just immediately notices that the height has already been computed and it does nothing. So yeah. So after the first time, so like all calls except for the first one, they all execute in big O of 1 steps. Because all they do is they notice this and they just stop, right? They do nothing and they never look at any of this stuff, right? So only the first time it does this. But so anyway, like for all of the, except for the first call, we're getting this many per call. So like this is kind of adding up in total, like big O of the out degree for all of the calls of that function except for the first one. It's all adding up to that, right? It's like one step per call, basically. Okay, but in the first call, okay, I mean, it does a few steps to just figure out, well, no, not really. I mean, it just, okay, this is like one step basically, right? And now it realizes we're in this case. Okay. So yeah. So this thing can be done in degree of V steps, where, so this is going to take some time to run this function every time, but each time it runs this function, the steps inside of this algorithm, I associate those to U. Like that is, computing the height of U, that's U's problem, right? Let's not, I don't count that when I'm computing for V. So like, anyway, I'm counting the fact that, so now I have to count steps to be like, so for every in degree, every in neighbor, I kind of count one step associated to V, I guess. But all of the kind of internal things here get associated to U. And then this part can be done in degree of V steps, because I'm just going through each in neighbor. computing a number and seeing if it's the biggest or not. And then this can be done in just kind of big O of 1 steps. So yeah. So in the first call, it kind of loops. Yeah, it does a loop which takes d minus of v, so that's the in degree of v, right? Steps. Okay. And all of the steps inside of that recursive calls, those are associated to the other vertices. So the steps inside the kind of recursive calls are associated to other vertices. Okay. So maybe I'll say big O of d minus steps, and then like it computes that max, which also is like big O of d minus of v steps. Yeah, so in total, you've got big O of 1 plus out degree of v plus d minus of v steps are associated with v, and then you get like big O of v of d plus the number of arcs of d steps overall, because like by handshaking, if I add these things up, that'll count every arc twice. Okay. Any questions about that? Okay. I think that, yeah, you got to be a little bit careful there to like not count these steps twice, right? Like you might say, okay, this thing takes at most a certain number of steps, and it's inside of this bigger loop, so then I would count that. But you should really only count those steps, yeah, kind of corresponding to that vertex, not count them for everybody. Okay. So yeah, this is kind of the idea of dynamic programming. I guess in some sense this is kind of closely related to what we did in Dijkstra's algorithm. Maybe Dijkstra's algorithm isn't quite dynamic programming, but these are extremely related ideas, right? So if, in Dijkstra we have some digraph or something, and we're trying to find the shortest path from S to T. Like a really bad algorithm would be to just like find a path, compute the length, go back a little bit, find another path, compute the length, and like keep, if I was just like going through all the possible paths, right, that's going to take forever. But so like kind of the clever thing about Dijkstra's algorithm, which is kind of related to this, is that you don't make decisions and find the path and then change your earlier decisions to find a better one, right? What you do is you don't make any decisions. You just say, okay, what's the shortest way I can get from S to somebody? I don't care about T, but just some other vertex. And you take like the shortest arc. And then you say, okay, what's the shortest way I can get from, so then this is like the set R of like vertices that have been reached. What's the shortest way to get from S to something outside of R? And then you say, okay, it could be through here and then out, or it could just be from S. And whichever those it is, you take that, right? And then you kind of enlarge your set of things you've reached. But at no point am I making a decision that I'm going to go this way to get to T, right? I could go that way, right? And then, maybe you kind of explore this way and this way. And only when you get to T at some point, do you finally make the decision that actually this was the best way to get there, right? So that's kind of the idea of dynamic programming as well, that you kind of keep all of your options open until at the end you can determine actually that was the best way to go. Okay, so anyway, this allows us to solve this longest path in a DAG problem. So now that we've solved this, if you could take another problem and reduce it to finding the longest path in a directed acyclic graph, then you've just solved that problem, right? So one strategy for solving problems using dynamic programming is to just reduce them to longest path in a directed acyclic graph problem. So yeah, I think there are some on your fourth assignment that that basically boil down to this, like you should just correctly define a digraph, and then like the solution to the problem will be the same as solving the longest path problem in that digraph. So if you can just think of the, you can kind of break your problem down into basically this, then you're good, right? Now, this isn't always the best way to do it. Sometimes you can reduce it to this problem, but there might have been a better way of doing it. So maybe let's see an example of that. So, okay, sometimes this is the best way to do it, and sometimes there's a better way. So here's a nice problem. Longest increasing subsequence. So your input is a sequence x1 n of real numbers. Okay, and the problem is to find the longest, let's say, strictly increasing subsequence. So yeah, this sequence of numbers, they can go up and down, like they're just an arbitrary assortment of numbers, and I want to find a subsequence where it's all kind of increasing on that subsequence, and I want that to be as long as possible, right? So I guess the first approach would be to just reduce to a longest path problem in a directed acyclic graph. So maybe I'll let you guys think about it. So what I want you to come up with is like a digraph D with n vertices. Okay. But I guess my question is, what would be the arcs of the digraph for this reduction? So let's say you've got n vertices, which are just the numbers 1 up to n. Any idea how I might want to define the arcs so that a longest path in D corresponds to a longest increasing subsequence. And I also need the digraph to be acyclic, but I think that'll come for free if you get the right definition. Yeah, I think we've got the idea that like, so I'll put an arc from I to j. So I want to do that if I is less than j and the actual like value xi is less than xj. So I guess that's my condition for making an arc. And then, yeah, if I have a path of like, let's say 5 vertices, that'll be like, if I start at the first one, the indices go up and the values go up. So then it's an increasing sequence of length 5, right? So yeah, this is not a bad approach. It's going to give you something, right? The thing is, OK, this digraph, it might have quite a lot of arcs. It might be as high as like big O, like kind of order of n squared. Like, you know, I can't really, like for example, if the whole sequence was increasing, then every pair would make an arc. So you could have kind of n choose 2 arcs. And obviously the number of vertices is n. So like just reducing to the previous algorithm, we get running time like big n squared for this. Because it's big O of the number of vertices plus the number of arcs. The number of arcs could be n squared. I don't know, right? It could be much lower, but I can't really guarantee that. But yeah, so now I claim that, OK, this works, but it's not the best way. So here's a better way, which is also using dynamic programming, but not just breaking it down to this. Oh, yeah, by the way, this, I never said that this digraph is definitely going to be acyclic, right? You can't have a cycle because, you know, as you're going along the cycle, the indices are going up, the values are going up, and then like you couldn't close the cycle, right? OK, so here's another way. So I claim, so here is a, so this can be solved in time big O of n log n, which is significantly faster than n squared, because logarithm is a very slowly growing function. Okay. Okay, so here's how I'm going to do it. So my goal is going to be, where I'm going to compute some function f where, yeah, f maps numbers 0 up to n to like negative infinity to infinity, and where f of I represents the minimum value of xj, so xj is in the sequence, such that there exists an increasing sequence of length I ending with xj. Or sorry, increasing subsequence. Okay, it's kind of a mouthful, but okay, so what I'm going to do is I'll start by initializing f of 0 to be negative infinity, f of I be infinity for I at least 1. Do I have this right? Let's see. Okay. This 0 thing, I equals 0, maybe don't worry about that too much. That's, I think it's just going to be convenient in this to have f of 0 be defined. But yeah, all of these other values, those are the ones that we kind of are interested in. And basically at the end of this, what we want to do is we're going to want to pick the largest index for which f of k is less than infinity. Or so largest index, let's say I, such that f of I is less than infinity. And that will mean, because like the larger values of I, being infinity means we haven't found any increasing subsequence of that length. Okay. Maybe I'll just write it and then we can see why this works. So for each, let's say j from 1 up to n, we kind of process xj as follows. Okay. So first we find the largest index I such that f of I is less than xj. Okay. So first of all, this is going to exist because f of 0 is going to stay negative infinity forever. So like I could be 0. And yeah, so there will be some index where f of I is less than xj, and we find the biggest such index. Now this actually sounds expensive because if I just took like I equals 0, I equals 1, I equals 2, I equals 3, and I computed them and I checked if it's bigger or not, that's going to take, now I'm going to get quadratic time. But this, the nice thing about this is that this can be done using a binary search. Because what the way this is going to work is that the sequence f of 0, f of 1, f of n will always be increasing. Well, non-decreasing. Okay. Do you know this like concept of a binary search? take the middle value, yeah. You know, take the thing in the middle. If it's less than xj, then I would like restrict myself to this half of the sequence, and if it's bigger, I would restrict myself to that half of the sequence and keep cutting in half. And this takes log n steps. So because we're using a binary search, this takes big O of log n steps. Okay, because you can only cut the sequence in half log n times until you get to only one element. Okay. And then once we do this, we're going to set f of k plus 1 to be xj, or sorry, I plus 1 to be xj. Okay, let's try to see why this works. Oh, and by the way, at the end, when we want to solve the problem, we would just find the largest I such that f of I is less than infinity, and output I, because I will be the length of the longest increasing subsequence. Okay, and this is going to take big O. Every step takes n log n time, or sorry, log n time. So let's try to see why this computes this function correctly. So at the beginning, it just says f of 0 is negative infinity, f of 1, f of 2, they're all infinity, which says that so far, if I wanted to know what's the, among all of the sequences of length 1 that I've seen so far, what is the minimum value of xj? And the thing is, I haven't found any sequences of length 1 yet. I haven't done anything. So infinity is the minimum, because I haven't found any. So then it'll process the first element of the sequence. It'll find the smallest index such that f of I is, the largest index with this property. It'll be 0, because f of 0 is negative infinity, f of 1 is infinity. So yeah, it'll find 0, and it'll say, OK, it'll then set f of 1 to be x1. So that'll say the smallest xj that I've found so far, where there's an increasing subsequence of length 1 that ends there, is just x1. OK, and then yeah, then it'll process x2. It'll find this largest index. So if x2 is bigger than x1, it'll realize that f of 1 is less than x2, and then it'll notice that x1, x2 is an increasing subsequence, and it'll set f of 2 to be x2. I'm not sure if this makes any sense, but I think this is doing the right thing. I guess what we could maybe do an example. So let's say what is my longest increasing subsequence? I'm thinking it's probably this, 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 and this. You're not going to do better than that, right? I think. But of course, we don't know that, right? But okay. So okay, so at the beginning of my algorithm, yeah, so let's suppose we don't know this, but it's gonna, hopefully it's gonna find it. Okay, so I first look at x1, and I try to find the index, the biggest index where f of I is less than x1. All of my f function, like it's just a bunch of infinities and negative infinities. So yeah, it finds that f of 0 is less than x1 and f of 1 is bigger. So what it's going to do is it's going to immediately just update f of 1 to be negative 3. Okay, so this is the step where we process the first element of the sequence. Okay. What this corresponds to is, so far, the longest sequence of length 1, among all the subsequences of length 1 that we've looked at, the lowest value that it ends at is negative 3, because that's the only thing we've looked at. Okay, so yeah, this one's been processed. Now I go to this one. I find the highest index where this number is less than 2, which is this one. I make that a 2. This stays the same. Those stay the same. And what this means is that so far the biggest, if I kind of scan this from left to right and I say what's the last finite number I see, it's this. And this tells me that, yeah, I've got a subsequence of length 2, negative 3 and then 2. That's increasing, right? So now I've processed this one. Now I go to this one. Again, though, I see this is the latest index of the function where this number is less than 0. So I'm going to update this number instead. And what this kind of signifies is that still, once I've processed these 3 vertices, my longest increasing subsequence is length 2, just like it was before. But this is better, right? So going from negative 3 to 2 would be stupid if you could go from negative 3 to 0. Because 2 is going to rule out everything that comes later, or except for this 4, right? But 0 is better at not ruling things out. So this is kind of saying that, so far, the best starting pair I've seen is this pair. I would never choose the 2 because it'd be better to choose the 0. So that's why, after processing the first 3 elements, this is my sequence. That if I wanted to take a length 2 sequence, it should end with the 0, not the 2. Now I look at this 1. This is the highest index where this value is less than 1. I update that one. Okay. And this signifies the fact that if I take the longest subsequence I can so far, I should just, I should add 1 to it, right? Okay, this one, take the biggest index that, what would it do? Okay. Right, so we take, this is the biggest, the furthest over number that's less than negative 1. And so it'll update this value to negative 1. What this signifies is that if I was taking a subsequence of length 2, the lowest possible second value on that subsequence would be a -1. Because, yeah, this would be your subsequence of length 2 with the lowest possible second value. Okay, then the last one, I'll just update that to a 4. Okay, and then to find the longest, longest thing. Okay, it ends up being, yeah, you take the maximum index for which that's not infinity. Okay. Okay, so what this is meant to demonstrate is that sometimes, you could just reduce this to like a problem in a directed acyclic graph. Might not be the best thing. You might need to actually analyze the problem you're dealing with and do it in a faster way, right? Okay, so that's like, I guess, 2 examples of dynamic programming. And yeah, so any questions about this thing? Yeah.
So for this version, it's faster, but you don't actually get the subsequence at the end. It's just it exists and it's this size.
Yeah, that's something I wasn't doing here, but I think you could do it. Like, I think you could keep that information. Yeah, you could keep track of like the parent of each element as well. So the reason this is faster is not because like losing information. The reason it's faster is that the kind of previous values that we need to look back at have a nice structure to them. This sequence is always going to stay ordered in increasing order. And therefore, if I wanted to find this value, this I, such that this largest I can quickly just cut this in half and like kind of do a binary search and find it. In the directed acyclic problem in longest path problem in a DAG, like your in neighborhood doesn't have any natural structure to it. Like, these things don't necessarily come in order. So, this is just taking advantage of the fact that these things are always in the correct order, and so I can quickly search through them. Okay. Whereas if you're just treating this as a longest path problem, you just look through all the in neighbors, and that's going to take longer, right?